Hello world, Microcats! We continue to work with the input-output expander. This time we use a 7-segment display and a flat membrane keyboard with 16 buttons. We turn on the power and try what happened. We press the keys one by one. We see that the 7-segment indicator shows the value of a pressed keyboard button. Additionally, I added LEDs where needed only for debugging and understanding the process of how the microcontroller program algorithm works. The keyboard works well, without delays and false positives. The only drawback is the lack of simulations pressing. The top 4 LEDs, which are constantly on, are actually alternating, but the key pulling rate is now very high. Let's see what happens at a low frequency. Once again, for understanding, this is a 7-segment indicator, this is a microcontroller, this is a keyboard, this is an input-output expander chip. It works via SPI with a microcontroller. Additional LEDs for power and data lines. We turn on and see how the LEDs flash slowly, one after the other. This is the alternate supply minus the supply on the supply line. These are vertical power lines from 0 to 3. The keyboard columns are different. The button for LEDs are information line indicators. We pressed the key 1. This is power line 0, information line 0. Press key 2. This is power line 1, information line 0. It is the same with key 3. We pressed the key 8. This is power line 1, information line 2. Press the D key. This is power line 3, information line 3. We have horizontal lines, each of which corresponds to these LEDs. Line 0 is LED 0, and when you press any button from this, the line will light up LED 0. Thus, the upper LEDs are indicators of the supply lines, which are vertical, where mills take turns. The horizontal lines are reading lines. All this is done by the input-output expander. Keypad power and read lines are connected to this expander. After we read a certain key, this data through SPI gets into the microcontroller. When he analyzes this information and issues a control signal back to the expander in order to be able to show the figure on the 7-segment display. That is, when we press the keys, the values of these keys are processed by the microcontroller and it issues a signal to display numbers in 7-segment form. Let's move on to the electrical diagram. A 7-segment LED indicator with a common cathode is used as an indicator. The connection diagram is shown in the table. The input-output expander is connected according to its datasheet. The int A pin is used. Thus, the total number of pins for communication with the microcontroller is now 5. An STM32 blue pill is used as a microcontroller. The input device is a membrane keyboard with 16 buttons. Its internal scheme is shown. The vertical lines of a keyboard are the power lines and the horizontal lines are the read lines. Let's consider the software part. Setting up the periphery. Setting up the MCP object. It is necessary to specify the pins for the CS and INT lines. We specify the hardware address and SPI interface, as well as a data handler function. This function will be called when a keyboard key is pressed. We initialize the keyboard settings by calling a special function. The input data processor is used to send a signal to the 7-segment indicator. The connection diagram is written here. In order to include the segments separately, we'll create a special array of translation values. Further, from the incoming symbol, we get its digital representation. We use a translation array and install the desired segments in port B of the input-output expander. The function of setting the expander in the mode of operation with the keypad 424. The keyboard has 8 pins, 4 of which can be called horizontal read lines, and the other 4 are vertical power lines. Their intersection defines the pressed key. They are all connecting to port E of the expander, so let's configure the expander pins in this way. We use the following algorithm: setting up pins, alternately setting lines, waiting for an interrupt signal from the expander, processing an interrupt signal from the expander, determining the pressed key, calling a custom handler. We write the data to the expander register one by one. See the datasheet for more information. The registers are configured, and now, if the button is pressed, when one corresponding read line, there will be an active 0, but for this it is necessary to power the lines. This happens through timer 3, turn it on, and immediately power line 0. Timer 3 interrupt solves 2 tasks. The first is the alternate powering of the lines, and the second is the increment of the number of the current powered line. In the update event, we check the number of a powered line and install it in the expander. In the coincidence event, increment the number of a powered line. Interrupt signal processing from the expander. The first thing we do is stop the timer 3. Next, we read the data from the expander. This is the triggered read line from the pressed button. We check which line is powered. We get the intersection of the lines, and this is the button what is pressed. We call a custom function to process the result. After that, turn on timer 3 again and continue on working. And of course, do not forget about the clocking of the input-output ports and peripherals. That's all, see you in the next video. Subscribe, Microcat!